You know, every single year, industrialized nations spend a staggering 5% of their entire income fighting a totally invisible, relentless enemy. I mean, it doesn't make the evening headlines, it's not crossing borders with tanks, but it is silently just eating away at our infrastructure, our vehicles, and our technology, costing us billions upon billions of dollars. All right, let's just dive right into this explainer. Think about two identical 1936 automobiles. They perfectly visualize the massive economic and physical stakes of material degradation. On one hand, you've got a classic car just rusting away in a field in Bodie, California. Its body was made of plain carbon steel, and its paint offered really limited protection against the elements. On the other hand, a 1936 deluxe Ford sedan, made entirely of unpainted stainless steel. This thing has logged hundreds of thousands of miles, yet its surface finish basically looks like it just rolled off the assembly line. The contrast is literally night and day. So we're going to take the seemingly boring inevitability of rust and transform it into this fascinating microscopic war for electrons that's taking place all around us right now. By the time we wrap up, you're never going to look at a rusty nail or a shiny car bumper the same way again. We're decoding the secret language of metals to understand exactly why things decay. Here's how we're going to break it down today. First, a tale of two cars. Then, the dance of electrons. Next, the hierarchy of metals. Fourth, measuring the voltage. And finally, we'll figure out just how fast does it rust. Kicking things off with part one, a tale of two cars, and why material destiny is a choice. That pristine stainless steel car we talked about, it survived hundreds of thousands of miles, while the plain carbon steel one rusted into absolute oblivion. And what this proves is that engineering choices dictate survival. The engineers behind the stainless steel Ford made a deliberate, calculated choice to use a material that heavily resists its environment. The others? Well, they relied on paint, a temporary barrier that eventually just gave up. In the world of materials science, destiny isn't left to chance. It's a calculated decision based entirely on how metals interact with their surroundings. Moving right along to part two, the dance of electrons, down on the microscopic battleground. So, what exactly is rust? You've seen the brownish-red flakes, you've probably felt that rough texture, but what is actually causing this massive physical degradation? Why does solid metal just seemingly vanish into thin air, leaving behind that brittle, flaky residue? Well, it's not magic, it's a highly predictable electrochemical transaction. It all kicks off with oxidation. Basically, you can think of this as a metal surrendering its electrons. It becomes the donor in this transaction. When a metal like iron oxidizes, it literally gives up its valence electrons. It goes from being this solid, stable, neutral metal atom to a positively charged ion that just dissolves away. And the actual physical spot on the metal where this surrender goes down, we call that the anode. But here's a fundamental rule of the universe for you. Those surrendered electrons, they don't just disappear into the void. There has to be balance. They're taken in by a receiver during what's called a reduction reaction. The location where these electrons arrive is called the cathode. So for any of this electrochemical action to happen, you absolutely need both, a loser giving up electrons and a winner snatching them up. Now picture a perfect setup of a galvanic couple. Imagine a piece of solid iron on one side and solid copper on the other, both just sitting in liquid solutions of their own ions. Because they're physically connected by a wire, electrons can flow right between them. And boom, the stage is set for our invisible war. The absolutely crucial takeaway here is that in this specific setup, the iron acts as the anode and just corrodes away, while the copper acts as the cathode and actually builds up material. It's wild. The iron is dissolving, turning into liquid ions, and firing its electrons through that wire over to the copper side. The copper ions in the liquid catch those incoming electrons and deposit themselves as solid metal right onto the copper piece. Iron loses, copper wins. Simple as that. Which brings us to part three, the hierarchy of metals, or what I like to call the power rankings. This brings up a pretty critical question. How do we actually know who's going to be the donor and who's going to be the receiver? Well, scientists used the Galvanic series, basically the electromotive force series, to rank these metals. It's literally a power ranking for chemical stability. At the top tier, you've got your chemical VIPs, the noble metals, gold, platinum. They are highly inert. They stubbornly refuse to give up their electrons, which is exactly why gold stays incredibly shiny for millennia. Then in the middle, you have your intermediate guys, like nickel and copper. But down at the bottom, that's where you find the highly susceptible losers, like zinc, magnesium, and potassium. If you connect a metal from the bottom of this list to one at the top, that bottom metal is almost always going to become the anode and corrode away into nothing. Let's roll right into part 4, measuring the voltage, the actual driving force behind all of this. Okay, this is where it gets really fascinating. If we go back to that previous setup, but this time we swap out the copper for zinc, suddenly the iron becomes the winner. Because zinc sits lower on those power rankings than iron, the zinc gets forced into being the anode. It surrenders its electrons to the iron. The iron plays the role of cathode, receiving the electrons, and the zinc is the one that corrodes. It is a perfect example showing that a material's destiny depends entirely on what it's interacting with. Just like checking the voltage on a standard AA battery, the voltage generated between these metal pairs isn't just fun trivia. It is the fundamental driving force of corrosion. Engineers actually use the Nernst equation to take this voltage and predict whether a spontaneous corrosion reaction is going to happen. By factoring in the absolute temperature and how concentrated the ions are in the liquid, the Nernst equation tells us exactly how strong that push and pull of electrons will be. If the calculated voltage comes out positive, you better believe that invisible war is actively happening. All right, on to our final section, part 5. How fast does it rust? We're talking speed and polarization. Knowing a metal will corrode is one thing, but we need to know exactly how fast it's going to happen. We measure this speed using the corrosion penetration rate, or CPR for short. This is a brilliant little formula that looks at weight loss, density, area, and time to tell us precisely how many millimeters of a metal will just vanish into thin air each year. Now, for most engineering applications, an acceptable rate is losing less than half a millimeter per year. If your CPR is creeping higher than that, well, you've got a massive structural failure waiting to happen. But here's the catch. The reaction isn't instantaneous. It's actually controlled by a really cool phenomenon called activation polarization. Think of it kind of like a relay race, where the overall speed of the team is limited entirely by your slowest runner. All electrochemical reactions consist of a sequence of steps happening right at that tiny interface between the metal and the liquid. Whichever step requires the most activation energy, whichever one is just the hardest to complete, that acts as the bottleneck, and that bottleneck determines the absolute maximum speed your rust can grow. Let's trace this exact journey. Picture a hydrogen ion floating in an acid solution. First, it has to physically migrate all the way to the zinc surface. Then it has to receive an electron to form a single hydrogen atom. Next up, it has to find a buddy, another hydrogen atom, and combine to form a molecule. And finally, a whole bunch of those molecules have to group together to form a physical gas bubble that floats away. If forming that bubble takes the longest time, then the entire corrosion process can literally only happen as fast as those bubbles can form. And that brings us to our ultimate takeaway for this explainer. The science of corrosion shows us that decay isn't some dark, unavoidable magic. It's just a perfectly predictable transaction of electrons. We can rank the metals. We can measure the precise voltage driving the reaction. We can calculate the exact speed of the decay. We can even pinpoint the specific molecular bottlenecks slowing the whole thing down. Armed with this knowledge, we are no longer just passive victims of rust. So it leaves us with a pretty incredible question. If we can understand this microscopic battlefield so perfectly, how are we going to use this knowledge to engineer the completely indestructible cities and machines of tomorrow? Definitely something to think about.